Reminding you just of a few things that we were doing at the end of last time. If you remember, I defined gamma MR to be the set of all graphs that contain a clique of size R. We're trying to show that gamma MR cannot be obtained by a monotone circuit unless that monotone circuit is very large, which is equivalent to saying that we take sets E1 up to En such that these ones are the half spaces xi equals 1, and these ones are built on the earlier ones using intersections, unions, and complements. Then En cannot equal gamma MR unless n is very large. That's what we'd like to prove. And the strategy was to come up with some legitimate lattice L, so that means something that's to some class of sets where you've got a notion of a meet and a join, and that contains the sets E1 up to En, which I can rename F1 up to Fn. And then whenever you had a union of two earlier things, you took the join, and whenever you had an intersection of two earlier things, you took the meet, and complements aren't allowed here, so I've just accidentally mentioned complements without meaning to. So we sort of imitate the computation above, but stick inside L. And then the idea then is to do a two-stage process. One is to show that not that Fm cannot equal gamma MR, because that's not sufficient, but we want to show that Fm is a long way away from gamma MR in some sense. And what we do to do that is to say that Fm, and that Fm approximates Em sufficiently closely in some sense that then Em cannot actually equal gamma MR. And I proved, well, I sort of half proved a lemma to the effect of what one could do along those lines more precisely. But this time I want to sort of redo it actually, because I sort of tried to generate the lemma from the proof. But this time I'm going to do things in a more conventional way. I'll state the lemma and prove it. But I won't do the whole proof because a number of aspects would be very similar to other ones. So I'll do it and then I'll do most of it. Let me remind you of some notation. So let's suppose we've chosen our meet and our join. Then we define error sets. We're going to assume that we have chosen these meets and joins in such a way that A meet B is always contained in A intersect B, and A join B always contains A union B whenever A, B belong to this connection L. And having done that, we define the error sets to be just the differences. Wrong way around. And the other one. So all this I said last time. So now let's state the lemma. What should I say? Let everything be as above. And again, as I say, I will be producing something written that will be slightly more precise and that, so I won't, then I'll say, assume we have a collection of sets. We have other ones that are produced in such and such a way and give full statements. But anyway, I've just told you what the setup is. So given that setup, then there exist pairs AI, BI, I equals n plus 1 up to m with A AI and BI coming from the lattice L, such that for every R less than or equal to M, we have that ER take away FR is contained in the union I equals M plus 1 to R delta cut AI BI, and FR take away ER is contained in the union I equals M plus 1 to R delta cat AI BI. And we can actually say slightly more than this, but there's no need. So the slightly more that one can say is you can look at whether R is whether ER is a union of some earlier things or an intersection of some earlier things, and then you only need one of these according to which you choose. But let's I've sort of proved half this lemma, so let me try proving the other half of this lemma in this more formal thing, and then so suppose that EM, I should say induction on M. Suppose that EM is ER. I'm going to do the intersection ES case first of all. Then Fm equals FR meet Fs. So Fm minus PM equals FR. What's contained? There's two steps in one, since we've sort of seen it already. Which is contained in, right, this set here is just the it's not the one I wanted to do first, but it's just, actually it's not such a problem to do this one first. So the empty set union FR minus ER union FS minus ES, and maybe the problem is I'm just wondering whether I've got these two the right way around. I think I've got them the wrong way around, actually. I have, yes, okay. That's why I was confusing myself. Okay, so in particular, I got them the opposite way around what I said in the last lecture. Okay, but that's fine. So in that case, forgot what the four cases are. So Fm minus Em. Alright, so and let's do what EM minus FM is. So this is not quite the way I organised it last time. But so also EM minus FM is a subset of ER intersect ES minus FR intersect FS union FR intersect FS minus FR meet FS, which is contained in ER minus FR union ES minus FS union delta meet FR FS. So in this case, we just set AM to be FR and BM to be FS, and we're done by induction. Just to see why we're done by induction, this one is contained in this union for R, and the other one's contained in the same union for S, and we just add on the set AM, BM, and that increases the union to what we want for M. And a similar argument that's the case. So EM equals ER union ES. So we put it all together, and we get that, as I say, if you take ER and take away FR, that will be contained in a union of sort of intersection style error sets, and if I take FR, take away ER, it will be contained in a set of union style error sets. So now, here's what I'm going to sort of lay out a bit more of the strategy of the proof. Before I say what the lattice L is going to be. Because the definition of lattice L, if you just snap it down, is extremely mysterious looking. But if I make a few preliminary remarks, then I think it will help a bit. So I just want to say what the lattice is hoping to achieve. And in particular, there's one aspect of the proof that's not completely obvious. I got the statement of the lemma. Yes, it's there. So the idea is going to be that every element of L is either just a set of all graphs, or equivalently just the whole of 0, 1 to the n. And if L is a set of, so in that case we could say if our Fm happened to be that element, which is a set of all graphs, then Em certainly isn't a set of all graphs if Em is to equal gamma mr. So gamma mr is a set of all graphs that contain a clique of size R. So gamma mr in particular, for instance, this is an important point, gamma mr does not contain any complete R minus 1 part graph. Sorry. Yeah, that's what I mean. Because a complete R minus 1 partite graph doesn't contain any clique of size R. So that's a little trivial remark. But the reason for the trivial remark is that if we chose our approximating sequences and ended up with Fm being the element of L that was in fact the whole of 0, 1 to the n, in other words, it included all graphs, then Fm would include every single complete R minus 1 partite graph. But Em we would want to contain no complete R partite graphs, and therefore we would want FR minus ER, which is this union of error sets, to contain all complete R minus 1 partite graphs. So we will try to devise the lattice in such a way that each of these error sets contains only a small number of complete R minus 1 partite graphs. So if we can do that, if each error set contains an exponentially small proportion of all R minus 1 partite graphs, then if this contains all of them, then we need exponentially many of these error sets for this containment possibly to be true, in the case where that's all graphs, and that's the set of all graphs that contain a Clique of size R. So that's one requirement. And what's the requirement in the other direction? Well, in the other direction, so let's say if L is all graphs, then L contains all complete R minus 1 partite graphs, which is a contradiction. So if Fn equals L, we get a contradiction. If every error set of this type contains very few R minus 1 partite graphs. And in the other direction, we're going to try to choose. So now the second case is when L is not the set of all graphs. So if I've got a set that's not the set of all graphs, we're going to try and devise the lattice L in such a way that it only contains at most half the cliques. If it only contains at most half the cliques, then I can say something very similar. If FR only contains half the cliques, or FM rather, only contains half the cliques, and EM contains all the cliques, then between them these error sets have got to contain at least half the cliques. So if we can prove that each error set of this type only contains a small proportion of all cliques, then we get a contradiction of the other kind. I won't bother writing that down. Or maybe say second case, I would say. To try and devise that L isn't all graphs, then L contains at most a half M choose R cliques of size R, and then we're done, as I say, if we can show that these error sets only contain a small proportion of all possible cliques of size R. Of course, so the main point about this is that it sort of helps because it allows one to choose, sort of separate out the two things that we're doing. So we can try to deal with cliques by choosing a meet operation and joins, and R minus 1 partite graphs by choosing the join operation. And in some sense, that's sort of why, or one reason why, things work better in the monotone case. In the non-monotone case, when we had complements, we would be forced to come up with some definition of meet that more or less gave us something very similar for the join, because once we took the complements, we'd be turning the meet into the join or something like that. So this idea of just separating out the two things wouldn't work. But that still leaves it completely open how on earth you choose L and these operations. So I'm now actually going to draw a slight sort of rabbit out of hat, but I think that they're rather natural ones. So the first one, we know that L contains monotone sets. I haven't quite said what a monotone set. A monotone set is a set of graphs such that if you've got a graph that's in the set and you add some more edges, then you're still in the set. Now, if you've got a monotone set, then it's determined by its minimal elements. If I know what a minimal graph is in a monotone set, then the monotone set is the set of all graphs that contain one of my minimal graphs, obviously. So it's very helpful to think, when you're thinking about monotone sets of graphs, about what the minimal graphs are in that monotone set. Now what we're trying to do is find a class of sort of simpler monotone sets. So we could say, one way of simplifying could be to say that we're going to take monotone sets whose minimal elements have a particular form. Just as a sort of test of how natural this is, can anyone guess what a sort of naturalish form in this problem for the minimal elements of a sort of slightly restricted set of graphs might be? So every minimal element is a something, some kind of graph. Any guesses about what that kind of graph might be? I don't care if it's wrong. I just want to see whether how many guesses it takes to get it.
A complete R minus 1 parsec.
Okay, complete R minus 1 parsec. Any other guesses? I claim there's only one more guess.
Complete R.
Complete R parsec?
That was the same guess as the previous one. Complete R parsec, sorry. A Clique. Okay, we got there in 3 guesses. So that sort of proof that this is not a totally wild thing to do. So the sets in curly L will be sets whose minimal elements are cliques. Actually, more to it than that, but L is not going to be just the set of all graphs, the collection of all sets of graphs whose minimal elements are cliques, because, for example, gamma MR is an element of that, and we're trying to prove that gamma MR is not close to it. So we've got to be a little bit, and that's one way that maybe the clique thing is, at first, it feels a bit strange because we're sort of trying to avoid cliques. What that tells us is that we cannot afford to let a set in L be of the form, an arbitrary set of the form, the set of all graphs that contains a clique in with vertex set belonging to this collection of sets. But nevertheless, here's a piece of notation which we're going to use. So if A is some set system, that, by the way, is notation for the power set of a set of inputs from 1 to n. I'm going to use this power. Then define to be the set of all cliques, so a set of all graphs containing a clique with vertex set in A. Now, as I said, gamma MR is precisely this set when A is the collection of all sets of size R. So we've got to restrict somehow what sets A we're allowed to choose to get into curly L. Another point is that we want any element of L either to be the whole of 0, 1 to the n, i.e. to contain all graphs, or to contain at most half the cliques. So one way of getting a handle on that is to show that A doesn't contain too many minimal elements of any given size. If we could somehow manage to ensure that a set A, so in other words, that whenever we've got a set A such that that belongs to our lattice, if we've somehow got a proof that A doesn't contain too many minimal elements of any given size, we can then argue that the set of cliques that contain one of those minimal elements is not too big. So that suggests what we want to do is somehow restrict the sets A that we can choose in some sort of way that will guarantee that there aren't too many minimal elements. By the way, we might as well, this is a total will-over, we might as well assume that the sets A are upsets, and if you've got a set in A, you've got all sets including that set. That's a very convenient thing to do. Now the next idea, again I'll draw out of my head, but I think it is a rather natural one, which is to define the notion of simplicity of A in terms of a closure operation. So what we're going to do is we're going to say, given a set A, if you've got a bunch of sets with some property and another set over here, they're related in a certain way, then we say that these sets generate that set, and that set comes into here. And whenever you've got a set, you chuck in every set that you can generate from that set. And then we say, we'll insist that our sets A are closed in some funny operation. That again, I think, okay, it's not maybe the first thing that comes into one's mind, but it's not a completely, once you say it, sounds reasonably sensible. So let's just think a little bit about, I'm now going to tell you what the closure operation is, but I just want to say one thing. If you've got a closure operation, then the obvious definition of this jointness is, well, the union of these. Let me just write what the union is. That's easy to check. The set of things that either contain an element of A or contain an element of B is a set of things that contain some element of A union B. Trouble is, A union B is not necessarily closed if A and B are closed. Unions of closed things don't tend to bear nothing, but intersections of closed things do. So what would be a sensible definition of the meet? Obviously, just take the closure of. That's going to be a pretty obvious thing to do. Now, what is the closure of A union B? Well, you start with A union B and you say, I can generate this, I can generate this, I can generate this, and so on, and I'm going to have some definition of what I'm allowed to generate. In order for, what is the error set going to be? It's going to be this, take away this. So it's going to be sets of things that contain a clique that's based on the closure minus a set of things that are based on the set itself. So the error set will be all graphs that contain a clique that's in the closure, or whose vertex set is in the closure, but not in the union itself. So we want to devise our way of generating sets in such a way that each time we generate a new set, we won't produce too many complete R-1 par-type graphs. Now here's the thought process that I think was was there somewhere. But you might as well actually define as your closure operation, I am allowed to add in to a set anything as long as I don't introduce too many R-1 par-type graphs in the process. That's not the definition I'm going to give, because it's a little bit hard to analyze. The point is actually also this works with our previous wish to have as few minimal elements as possible, because the more you're allowed to generate, the fewer closed sets there are going to be, and so it sort of only helps if we're trying to prove a statement like every closed set doesn't have too many minimal elements of such and such a kind. Luckily, this was something that mystified me until recently. It appeared that the definition was doing two things, and absolutely miraculous that it managed to achieve two different things. But then suddenly it sort of occurred to me now that actually they work in the same direction and not pulling against each other. The more generous your closure operation, the better it is for minimal elements. So you might as well make it as generous as you can, subject to the condition that each time you add something into the closure, you don't introduce too many R-1 par-type graphs. So the actual definition will make sense after I've proved that the closure operation doesn't introduce too many R-1 par-type graphs. You'll see how it actually just comes in beautifully to prove it. But it's not obvious completely in advance. But it does feel like the sort of thing that somebody could have come up with when you see the proof. So here it is, after all that preamble. I'm going to say got a collection of sets, A1 up to AS, not necessarily distinct. I'll say that they generate A, or I think in the paper that I got this from, they say entail A. That's why it has this notation. But anyway, we'll say that they generate A if AI intersect AJ is a subset of A for all I not equal to J. We also wanted our... Okay, so I then say A is closed if obvious thing, those belonging to A and generating A. That implies A belongs to curly A, and the closure is the smallest closed set containing A, which, as usual, you can think of in two ways. Either you start with A and just keep generating until you can't generate anything new, or you take the intersection of all closed sets A and you get the same thing. Actually, also, we're only going to be thinking about, this is another important, actually, aspect of the whole thing, that the sets curly A that we take, although I said they were closed upwards, actually we're only going to be looking at sets, set systems whose, the sets of which have size at most L, and L and S are both parameters that I haven't chosen and will be optimized later on in the proof. So now what is curly L then? Curly L is the set of all sets like that, such that A consists of sets of size at most little l, and A is closed. And the mean of two elements of L is a fairly natural thing. By the way, that's not quite the same as just the intersection of this with this, as we'll see later on. But you can just think about that and you'll see it's not the same. And join, I've already defined this actually, but that before I told you what the closure operation was, is that. As I say, when I first saw that, I thought that was really quite a lot to take in all at once. I hope that sort of gives you some idea of where it's going. Something I still do find a little bit mysterious is, once you see why this closure operation helps you with R-1 part A graphs, it doesn't feel quite so odd. The one thing that does still feel slightly odd to me is that there's a very neat proof for the number of minimal elements of a given size in a closed set. And that's what I'm going to do next. But by the way, just notice that this definition as given automatically implies that closed sets are sort of closed upwards, because you can just take all of A1 up to AS to be the same set, and then they generate any set that's bigger than that set. It's a matter of convenience. Another thing, actually, what does one do about singletons? If you've got a single vertex, when do you say that a clique contains that vertex? You might say that a clique contains that vertex if and only if that particular vertex is in the clique, so to speak. But you might also take the attitude that that vertex has no edges, and so the clique automatically contains it. Funnily enough, we will take the second attitude. So we're not going to be interested in, well, the way they put it in the paper, we will assume that if curly A contains any singletons, then it automatically contains the empty set, and therefore is the whole thing. It's just a technical convenience. You can consider that part of the closure operation if you like. That's the way they do it actually. But alternatively, I suppose we could say L consists of either the entirety of 0, 1 to the n, or these things, but now A is only allowed to contain sets of size 2 to L. So let's now, with that small technicality mentioned, let me give a lemma. The number of minimal elements of A of size k is at most s minus 1 to the k. One can get a little bit of a feel for the closure operation by first proving that this is best possible, if true. And so let me just quickly do that. It's not needed for the proof, but it's a nice remark. I should also say, I haven't said this yet, but the proof that I'm giving is an extension of Razborov's original argument, or modification of Razborov's original argument due to Alon and Bopana. So what Razborov did, I think I haven't said this, so Razborov got superpolynomial lower bounds, and that was the big problem. Alon and Bopana noticed that you could change his definitions a bit of the lattice and actually get, Razborov I think got something like an n to the log n sort of bound, but Alon and Bopana get something like e to the n to the 1/6 sort of bound, so exponentially large rather than just super or exponential in the power rather than just superpolynomial. Okay, so let's just see why it's best possible. You just take sets. I won't write it down properly. And I'll take A to be the set of all A such that A intercept Si equals 1 for all I. So I take K disjoint set of size S minus 1. I pick an element out of each. Obviously, the number of sets I can pick if I do that is S minus 1 to the K, because I've got K sets of size S minus 1 from which I have to pick an element each. And why is that closed? Well, let's suppose I choose A1 up to AS. Oh, wait a minute. Yeah, let's suppose I choose A1 up to AS, and they are minimal elements of curly A. Hang on. I'll come back to this. So this is proving something slightly different. Let me go. I'll come back to what I was trying to do there. Let me go first on into the proof of the method, because that example is illustrating something that's very, very closely connected with the lemma, but not quite the same. So let curly F be the set of minimal elements of A curly F has got a certain property, which is that if A1 comes to AS and A belongs to curly F, and if B is a proper subset of A, then there must exist I not equal to J, such that what? Well, if A is a minimal element of F and B is a proper subset of A, B can't be a minimal element of F. Or can't be an element of F, I mean. So in particular, if B is not an element of F, it can't be generated by A1 up to AS because A is a closed set. So it must be the case that AI intersect AJ is not contained in B. Because if every AI intersect AJ were contained in B, then these would generate B. So B would belong to curly A. So A would not have been a minimal element of curly A. So that's a particular property of F, and we'll call that property PSK. So that's the property that whenever you take S elements of size K, well, it's a property that's applied to set systems where the sets have size K. Whenever you take S off from another one, you cannot get it so that all the intersections belong to a given proper subset of that other one. So what I really wanted to say with this example was that so we shall prove that every F with property PSK has size at most S minus 1 to the K. Okay, so this is what the example shows. Here is an example, not for the curly A, but for the curly F, of a collection of sets that has size S minus 1 to the K and does have property PSK. And that's because if I choose sets A1 up to AS and A, and then I choose B that's a proper subset of A, then B can't intersect all the sets S1 up to SK. So let's suppose B doesn't intersect SJ. So but each of the sets A1 up to AS does intersect SJ. There are S of these sets. SJ had S minus 1 elements, so there must be 2 of these elements, AI and AJ, that intersect SJ, sorry, A, P and AQ or something, that intersect SJ in the same element, and therefore there must be 2 of these sets that intersect inside SJ, which means that they're not contained in B, because B has empty intersection with SJ. Okay, so there's just a simple example that shows that this statement about this combinatorial property that arises in the proof is best possible. So we're going to prove this by induction. So I'll let... First of all, if S equals 2, it's induction on S, and AB belongs to curly F, then AB certainly entails A intersect B, because all possible intersections of these are such that they intersect B. So A intersect B can't be a proper subset of both A and B, otherwise it would contradict the minimality either, or you contradict minimality. So, sorry, of either, I mean. That A must be B. In other words, you can't have two elements. I'd better put that the other way around. If I've got two distinct elements of F, then they entail their intersection, which will be a proper subset of at least one of them, and that will contradict the minimality. So now let's do the general case. And this was the example I'm referring to when I say that it sort of comes out so neatly that it's slightly mysterious, given that some of the property is more devised not for this bit, but for the R-1 part-type products. So let's just pick any old element of curly F, and for each subset of E, let curly F C be the set of all A minus E, such that A belongs to F, and A intersect E equals C. So everything has some intersection with E. We'll take all the ones that have intersection equal to C. The claim that FC has property P S minus 1 K minus C. Remember, all the sets in curly F have size K, so K minus C is just the size of these sets, A minus E. So let's prove that by contradiction. So if not, then we can find A1 minus E up to A S minus 1 minus E, and A minus E and B subset, proper subset A minus E, such that this is always the case. But then AI intersect AJ is a subset of C union B, which is a proper subset of C, a proper subset of A. I should say these all belong to curly FC. So when I put C back in, I get elements of F. And that doesn't quite contradict the fact that F has property SK, because I've only got S minus 1 sets there. But I can also add in one more set, and that's the set C itself. Sorry, not C itself, but it's the set E itself. But also E intersect AI equals C, which is a subset of C union B. So the sets A1 up to AS minus 1 and E between them contradict property F is supposed to have, so there's our contradiction. And now let's just do a few calculations to see what bound that gives. Size of n is at most the sum over all subsets C of E of S minus 1 to the K minus C. And that's less than or equal to the sum size E. J, that's I'm going to count all sets of size J. S minus 1 to the K minus J. And E has size at most K, so that's sum less than or equal to sum Kj S minus 1 to the K minus J and the binomial theorem. Sorry, it should be S minus 2 for the inductive hypothesis, I beg your pardon. And then the binomial theorem tells us we've got S minus 1 to the K. So the idea of the proof is just simply partition F up into these FCs, apply the inductive hypothesis to each FC. Prove that FC has a property 1 down, apply the inductive hypothesis, add them all up again, and you get the answer you want. But that's so sort of tidy that it's a little bit of a surprise. Next time we should finish the rest of the proof. I thought I was going to do much more than this today, as always. But once we've got this lemma about a number of minimal elements, then proving facts like either you contain all the graphs or you don't contain very many cliques is quick, as is the proof that the intersection style error sets are not very big. And then the proof for the R minus 1 quasi part is not too long either. So next time, unless things go badly wrong, I should finish this proof, I think. And I would like to say a few informal words about why general circuit complexity lower bounds are much, much harder than monotone ones. Not just people find them harder, but they're provably harder in a certain precise sense. Things like that. So then after the lecture after that will be when I'll probably get on to starting to talk about quantum computation and leading into short